So I hope that you have seen that I listed for you both in Canvas and I think maybe in an email, and I know in a WhatsApp post, a series of 9 time value of money videos, which videos run from I think about 5 minutes to one of them is like 24 minutes, and I apologize for that. And that's the whack one because there's so much involved in it. But they're averaging 9-10 minutes each. You don't need to actually view all of them. I have them there because you should have been exposed to time value of money metrics by now within your program. And if you have, they're nice little reminders for you. It's a little brush up, if you will. But if you haven't, then you can take the time to go through them because I go step by step. And I recorded these specifically for the work I'm doing here in the Gore School of Business. So I didn't pull them off of YouTube. These are me, and they're giving examples that are relevant in the way that I talk about these things. So with that said, I'm going to kind of breeze through certain elements that come from those videos and the PowerPoints that I use as their foundation, but I'm not going to do a lot of deep diving into them. I'm going to expect you to either have that experience behind you or do it on your own. In fact, I even asked that you try to do so in preparation for tonight. And if you have questions and issues, then I'm happy for us to light WhatsApp up or have another video session or whatever we need to do to make sure that you're comfortable with time value of money. The question is going to come, why do I want you to go through the actual equational metrics? One of you asked, I think it may have been you, Taylor, had asked about using the TVM function within Excel. And we're going to do that. In fact, I'm going to expect that by and large, you're going to rely on Excel on your calculator much more than you're going to rely on the algebra. What I've learned, though, over the years is if you don't have a decent grasp of the algebra, then you can't command how the Excel and the calculator function supports you very well. You don't understand how to put things together. So I'm looking at this from wanting to make sure you've got an exposure of the algebra. I'm then going to assume that when it comes to problem sets, assignments, quizzes, etc., even tests that we could possibly have, you're going to use your calculator or Excel. You're almost certainly not going to use the math, but I got to make sure you know the mathematical underpinnings. I hope that's okay with you, and if it's not, well, bummer for you, get over it, okay? All right, so here are the elements we're going to talk about tonight. So time value of money metrics, we're going to look at present value, net present value, internal rate of return, modified internal rate of return, payback, discounted payback, and profit index. We'll look at a multi-column evaluation structure. And by the way, the present value, net present value, etc., the multi-column evaluation structure is preparation for the next Excel assignment. And you'll see these. In fact, some of you have already gotten a head start on that. We'll talk a little bit about valuation equation forms, but we're only going to talk a little bit about those. We'll take a deeper dive into them next week and again the week after. I'll probably end up introducing you to some Excel templates and try to help you understand what not to do with them. And then here I'm just reminding you the assignments coming up. Excel 2, part of the using CAPM and WAC problem set, and then homework number 1. Okay, and every time I show you an assignment for homework, know that there's a practice homework that goes along with it. You don't have to do the practice homework. There's nothing that says you need to go through that, but it gives you the opportunity to practice on the equations and such in an environment where points aren't building up towards grades, etc. And I think I give you more than one a shot at the homework assignment when you do the actual quiz. I think I give you 2 of them, and I believe that I don't give you a time limit, which means that you could take all week if you wanted to. I hope you have better things to do with much of your week than that. And honestly, sometimes people will keep those open for a lengthy period of time. These aren't tests. These are there to make sure that you're practicing the metrics, because if you don't practice the metrics when it counts, then you're not going to be able to replicate them. Okay? They also bring up lots of really good questions as you guys are working through them that I then get a chance to answer. Let's actually go directly to this using Excel templates now, because we're going to spend just a moment there. So you probably have already seen this. This is one of my websites. And that, by the way, is my sweet wife. I have this photograph here with both of us. Sadly, it's a couple of years out of date at this point, but I like it because I like to look at her more than I like to look at me. And so, so that's why we all get to see my wife. And then I have for you these different Excel templates. Let me make sure that you see a problem that I don't want you to get stuck with. Let me just choose one of these. I'll open up Farm Hill Group. You guys are going to see the Farm Hill Group as an assignment here at some point. And you're going to recognize the structure of the Farm Hill Group because I structure these exactly the same way I structured some of the rest of your work. But there's a lot more going on here in the Farm Hill Group, as you can see by this matrix. We will not be replicating this matrix, okay? But we will be doing some of these forecasts, and we will be running down to values. Let's see if I've got, yeah, I do. And you're going to, some of you have already started to see this kind of a construction. Here's one of the things to be aware of. Some of these different templates are structured slightly differently. For example, the structure that we're going to use when we get to forecasting, in this field, it's net working capital, and in this one, it's fixed assets, just exactly as I have this one set up. But in some of them, this column is change in net working capital, and this column is change in fixed assets. These different structures do not give the same outcomes. I can't tell you how many times I get to find people pull one of my templates, start to dump values into it, not realizing it's a different structure. We sometimes are calculating the revenues differently from different growth rates. Sometimes they're persistent, sometimes they're not. Sometimes this is 3 years, sometimes it's 2 years, sometimes it's 7 years. So when you pull one of these, I have no problem with you picking one of these up and using it. I mean, that's what I have them for and linking them for you. Just make sure that if you're using a template, that you understand what's going on in the template and modify it based upon the scenario that you're dealing with, which means you've got to understand what's going on, and that's why I have you build these models for yourself, so you do understand, so that when you pick something up, you can modify and manipulate it as much as you need to. Any question about that? So use them, but just be aware of what you're using compared to what you're trying to accomplish. That's all. Okay. So let's go back to the PowerPoint. So we're going to recognize that there are two very basic present value equations. And these are actually the same equation, it just doesn't quite look like it. The first one is present value equals some beta t, and beta B stands for benefit. Could just as easily stand for cost. It's some cash flow. So beta t at divided by 1 plus a discount rate to the power of t. It's important to note when you see this kind of equation, the t subscript in the numerator is simply a descriptor. It is not an operator at all. The t subscript in the denominator, on the other hand, is an exponent. So it's active, and the one in the numerator is not, okay? And beta simply means whatever cash flow we're dealing with. So here in this very simple equation, this would be a one economic exchange. So we have the present value today of some number that we would receive at some point in the future, divided by 1 plus discount rate to the exponent of the number of periods between now and the time we expect to see that. Now you might say, well, wait a minute, that sounds a lot like it should be a future value. And it would be synonymous with a future value, because a one-time benefit received at a point in the future is a future value, right? So I don't care if you call this beta t, cash flow t, future value when it's the one-shot scenario. I care that you understand how it's affecting you. So the next one we have then is really the same equation, but it's for multiple periods. So where I have in the first equation something right now and something at a point in the future, in this second equation I have something right now for which I want a present value, and it's going to be equaling the sum of some things happening over periods of time in the future. So think about this. We're moving this to the point where we can analyze elements within a company. We can analyze maybe even the value of an entire company or a project in the company or some scope that you've been given as a manager. Well, we know that we probably can forecast our revenues, right? If we're thinking about a project in the company. Hopefully we can forecast our revenues. And we can forecast our expenses, which means we should be able to forecast some EBIT or some cash flow of some kind. And we're going to have that for some successive number of periods. Maybe we have it in perpetuity. Maybe we have it for 4 years and then close it down. Maybe we have it for 5 years and then sell it off. We have it for some period of time. And under the premise that an asset's value, present value, is the sum of its expected future cash flows discounted for rate and time, this equation will handle that scenario where we have a beta that's a cash flow, a T that's period of times, and an R that is simply a discount rate. If we're looking at this from the perspective of the firm, what is that R? What's the name that we give that R? We give it, well, we call it WACC. If we're looking at this from the perspective of the firm, the discount rate is the firm's weighted average cost of capital. We call it WACC, okay? If Heather walks in here and says, well, Rick, I don't care what the company's cost of capital is. I'm a seasoned investor, and I have a hurdle rate that I require of 16%, the required return. As an investor, if I don't believe I can credibly earn 16%, I don't open up my checkbook. And in which case, Heather's discount rate as an investor wouldn't be WACC, it might be her required rate of return. Realistically, if Heather is only going to be investing her capital, not her time, not her relationships, not her social network, etc., just her money, should she be able to expect to receive a return much greater than WACC, or should she expect her return to be not too far off of WACC? Well, tell me what WACC is for a minute. Can anybody give me kind of a definition? Not the equation. Don't go through all the numbers. You'll poke something sharp in my eye if you have to do that, right? But what's just kind of a common definition of WACC?
Is it the cost of carrying that cash for specific periods of time?
Well, it's the opportunity cost of the firm's capital components. Cash may well be one of them, right, Jason? Debt's one of them. Common equity is one of them. Preferred equity is one of them. And if we have accurately assessed those costs using prescient market value constructions, both for the cost and the value to get the weights, then the weighted average cost of capital should be the reasonably expected return that an investor would receive if the investor acquired all those capital components. Now, if the investor only acquired a common equity, it would be different. That'd be RE. Or only acquired debt, it would be RD, and so on. So if somebody comes in, Heather comes in and wants to buy the whole company, debt, preferred, common, the whole bit, Heather, if she's only investing her capital, could reasonably expect to earn WACC because we've rigorously assessed what those capital returns, i.e. costs, should be. So I think it's reasonable for Heather to want something a little bit more than the cost of capital because she's a capitalist and she likes to get an economic profit. But if Heather sees that there's a cost of capital at 16% and expects to get 30%, then she's either thinking she knows something that the market in which we made our assessments doesn't know, or she's expecting to invest something more than just her capital. She's investing time and relationships and energy and contracts and connections, etc. Does that make sense? We'll hit that a number of times. In fact, you may recognize that that's the second or third time we've experienced that little diatribe together. But we'll go through that more than once again. So let's give an example or two to some of this. So this is the single shot transaction, so one economic exchange. And I'm saying that our benefit is 100, our discount rate is 6%, and the number of periods of time is 5, and I'm using 5 years in this case. So know that if we're expressing time in years, we need to express rate in years, and we need to express benefits or payments in years. Think back to the market value of debt equation. Same kind of rules, okay? I could express this in months. Maybe it's 5 years at 12 months per year, in which case my T would be 60, and my 6% would be 0.06 divided by 12, and my benefit would be whatever monthly payment or monthly cash flow I would get. But just make sure that you are conceptually consistent within your benefit or cost, we might call it payment, and your discount rate and your time structure. Well, in this case, I want to know the present value of some money. Let's say that Solomon has told me, hey, Rick, I could use a couple of bucks. And I know that 5 years from now, I'm going to be able to pay you $100. And I know that you look for a 6% return. How much would you be willing to loan me? Well, this is kind of an arcane example, of course. And I'm pretty sure that if Solomon was coming looking for a loan, it'd be a whole lot higher than $100. Otherwise, I'm not sure why you're wasting your time, Solomon. Maybe $100,000, okay? But in this case, I know that if it's $100 in the future, and I'm discounting it at 6% for 5 years, I know that the present value is $74.73 today. It's the present. So very simple. Let's extend that a little bit further. Let's use the summation. So we're going to add up a variety of periods of time, but we're going to use constant cash flows. So our beta will continue to be 100 for each and every one of these years. This would be synonymous with using the top line function in your calculator, and we'll get to an example of that in a few minutes. Our discount rate is going to be 6%. Our number of periods, again, is going to be 5. But notice here that I've got beta 1, 2, 3. Well, that shouldn't be 30. It should be 3. Whoops. Excuse me. 4 and 5. And I have values of 100 for each of those. So constant cash flows. But I also have beta 0. If I'm expecting that the value of the asset is going to be the sum of the discounted future cash flows, beta 0, or some benefits, some cash flow at time 0, would be the cash flow right now. Would I add a value of that into this equation where I'm thinking about future cash flows? I'm giving it a value of 0. Why am I giving it 0? Because the cash flow that exists today isn't in the future. It's because of work that's already been performed, cash flow already received prior to the acquisition of the asset. So if Casey buys this asset from us today, he doesn't get the cash flow that it spun off today because of the work done before he bought it. He gets the cash flow that it spins off in the future after he's acquired the asset. So I wanted to make sure that you saw the utility of a beta 0. We're taking it exactly as you would expect to the power of 0, and any value to the power of 0 is equal to what? 1. So maybe we could, if this was a net present value, and we'll get to one of those in a few minutes, if this was a net present value, maybe here we would put the cost function. Maybe we would put how much Casey was investing in this to acquire the asset as a cost function, in which case, if we did that, it would have to be a negative. And you'll see why that is a little more clearly in a moment. But we would take it at time 0, which means we're really not discounting at all if he's making that investment today, right now. Well, in this case, I've gone ahead and shown you that for each one of these $100 that we receive at different points in time, that they start out at $94, $89, $84, $79, $75, rounding them as we go through years 1, 2, 3, 4, and 5. I didn't put 0 here, but I guess I could have just as easily said 0, because this first one would be 0, would it not? 0 divided by anything is still going to be 0 or undefined. So I then am simply adding these up, and I find that if I'm going to receive $100 for each of the next 5 years, and I have a 6% discount rate, that the present value of that, discounted for rate and time, is $421.24. Notice that I get the exact same value here when I motivate this present value equation. This present value equation is a present value of an annuity. Does it look familiar to you? What's it look like, Casey?
Looks like part of how we valued our market value of our bonds.
In fact, it's exactly how you'd value the market value of the bonds. In the annuity equation, this would be called PMT. 6 would be 0.06 would be called R. 5 would be called N. This 0 would be called future value. Well, the $1,000 face value we get in a bond is in the future, right? This $100 payment is an interest payment or a coupon payment. So it's the exact same equation. But more importantly than that, the reason I put it here is we're going to look at your calculator's functions in a few minutes. And when we use what I call the top line functions, this is the equation the calculator is working through, not this summation, which is a little more complex, but we get the exact same outcome. Because algebraically, when we have a constant payment, a specific period of time, and a constant discount rate, this summation and this singular equation yield the exact same results. And not close to the same, they yield the exact same results. Okay? Let's go a little further. So here we have an example of a non-constant cash flow. So instead of every cash flow being 100, I started 100 and then 125, 150, 175, and 200. You might argue that, well, Rick, these are changing at a constant $25. And that's true, but A, they're not constant, and B, they're not changing at a constant rate. So $25 on top of 100 is 25%. $25 on top of 125 is less than 25%, and so on. So these are changing at a constant dollar amount, but they're not constant and they're not changing at a constant rate. And that's important here. So as I look at this, I see that I can work this out just as you would expect me to, and I know that it's going to equal $534.69. Now, I'm not taking the time to go through all this math because I think you can do that on your own, and some of you already know the math, so I'm kind of playing to a diverse audience that if I went through everything, some of you would say, oh my gosh, you're killing me, I know this. And some of you would say, even if I took a lot of time, hey, you got to slow down. So I'm going to expect you to kind of pick this up beyond the class structure that we've got. So we dealt with a one-shot scenario, a multi-transaction scenario with constant cash flows, a multi-transaction scenario with non-constant cash flows that were not growing at a constant rate. And then we're going to look at something called the Gordon growth model, sometimes referred to as the dividend growth or dividend yield model. And this is the sum of some cash flows, or betas, divided by 1 plus r to the t. But in this case, if those cash flows are growing at a constant rate, then rather than have to add this whole series of values and find a value for every one of them, I can simply motivate this little equation. This little equation, cash flow time 1 divided by r minus g, gives us what I call a CV, or a continuing value, a present value, a terminal value. Those can be interchangeable terms for this. It gives it to us at time 0. This works off of that Gordon growth model that says some price at time 0 is equal to a dividend received the next period of time divided by R, or the discount rate, minus the growth rate of that dividend. In which case, the price at time 0 is a price of a share of stock, because that's the only thing that pays a dividend, and the growth rate, G, is constant. But there's one other element to this. Does anyone know the other condition in which this equation and this equation, are the same? What the additional component is? This simplified equation is perpetual. This takes an infinite number of cash flows, all growing at that constant rate in perpetuity. And it gives us their present value as a value today. Well, I love this equation even more because I can't come up with a summation when I have an infinite series of values, can I? Because the very moment I think I've added them all up, G comes in and says, well, Rick, you forgot the next one. And fine, and then Taylor comes in and says, you forgot the next one. We simply can't do it. It's a losing battle. But this equation, out to something like the 20th decimal place, This equation gives us the same outcome. This will be our friend, except for under a condition. Is it conceivable that a company's growth rate could be greater than the discount rate? So, Scott, I think you're with us. If not, then I'll let anybody else respond to this. So, Scott, you're an investor. Tell me what you don't like about this scenario. Here's an investment that's giving a positive cash flow, so nice positive income. That cash flow is growing at 10% a year, has done so from the first day this company started, and we're projecting it's going to do so forever, which is, that's hot, right? And the cost of capital for this company, for whatever reason, is dirt cheap. It's 2%. Well, I just told you a successful company with a constant, or a successful company with a track record of good cash flow, which cash flows are growing at a very healthy rate, and it's got a very low cost of funds. As an investor, Scott, does that seem at all appealing to you?
Yeah, so if something were to grow in perpetuity like that, it would eventually become the size of the world economy.
Well, true. In which case it may not be plausible, but if you thought it was, would that not be a very attractive investment?
Yeah, sure, but I mean, it's just not realistic.
Dubious. Okay, so let's change it. Let's say that it's got a 2% growth rate, okay? But that it has a 1.99% discount rate. That's maybe a little more plausible. Based upon this equation, this would have a value that's negative, because the denominator would be negative.
Right.
Right? So we have a conceptual problem. We like that it's got a strong cash flow. We like that it's got a cheap cost of funds. We like that it's got a very reasonable growth rate. And as an investor, I'm having a hard time finding the problem here until I work the equation and it gives me a negative outcome. What does that negative outcome mean? Any ideas at all?
Okay, can you hear me now?
Yes, Scott.
Okay. So that negative rate, doesn't that mean you're losing cash flow?
Well, what it means is that the cost of our growth is greater than the cash flow that we're spinning off to afford it. Yeah, so
Okay.
You're really close. In fact, you're going to see another phenomenon not dissimilar to this. We're going to see at times that companies will have a negative free cash flow. What does a negative free cash flow mean? Well, think about the equation for free cash flow. No plat plus depreciation minus change in net working capital minus net capital spending. Well, fine. I mean, that's easy to take a look at that, right? So let's parse it out. If that number is negative, and if it's negative because we have a negative EBIT, then this better be a very early stage company that just has yet to turn operating profit, or it's a company that's in some semblance of trouble, right? Or maybe it's a later stage company that's retooling itself and is reinvesting, and so it's for a very temporary period of time as a negative free cash flow. But negative free cash flow simply means that the company can't afford internally the growth that it's experiencing. It's committing more cash to growth than it actually is generating. So it's going to start to raid retained earnings, or it's going to need to have some other source of funds. It's going to have to raise some capital. So if negative free cash flow is a result of positive EBIT, that may not be all that bad. If negative free cash flow is a result of negative EBIT, you better look a little closer again and pay very close attention to this relationship between the discount rate and the growth rate. Because when the discount rate's greater than the growth rate, we're going to end up in a scenario where we have a negative value building up. And that may be very problematic. We'll use each of these later on, maybe not later on tonight, but later on. Any questions about where we've gone so far here? Okay, again, I know some of this is very simple for some of you, and it's frustratingly complex for others. You'll get used to it and go through the videos, spend time with me, with each other, WhatsApp, what have you, and we'll get you through this. So let's take a look now at the HP.